that's what the system looks like. We have a camera here, so we can look at the animal and tell when he, what we do is we look for the EEG activity to pick up, followed by the behavioral seizures. We found we get reflections on the window from the lights in the lab, so we blackened it out. That's what that little cone's for. All right, so we worked at 4, 5, and 6 atmospheres oxygen. This is showing you the variability of individual rats. This is the averages. So on average, about 60 minutes at 4 atmospheres to seize, a little less than 20 minutes at 5, and less than 5 minutes at 6 atmospheres. And here's what we saw. If we dove a rat 3 times on, say, day 0, day 7, and day 14, so over a 2-week period, you can see here's the ventilatory response the first time, and then the second dive, here you can see that, and then the third dive. And so he typically sees between 15 and 17 minutes at this pressure. And what you can see there is your eye can pick up ventilation starting to creep up each time before he seizes. And what you can also see is an earlier response here during compression. In fact, if you kind of average the responses, it's pretty typical of what we saw, where initially we start out in air and get our baseline. We then go to 1 atmosphere oxygen, and initially there's an inhibition, which is due to 100% oxygen inhibiting the carotid body chemoreceptors. And this is the hypoxic ventilatory response. But what happens if you leave hyperoxia on long enough, you can start to get the stimulation here. You actually see it creeping up a little bit in this guy, and then as we would compress him, we would see ventilation increase, but then it would decrease. Presumably this is due to the animal blowing off CO2 and feeding back and starting to blunt that hypoxic or hyperoxic, excuse me. I studied too many gases, hyperoxic ventilatory response. So this is what we would call poikilocapnic hyperoxia, because we're not regulating end-tidal CO2 at all. All right, so did we see this in all the animals? And the answer is yes, we did. This is the average data. This is tidal volume, frequency, and minute ventilation. And what you can see, this is the early response. So here we go from 20% to 100% at 1 atmosphere. Now we begin to dive them. And you can see there's this transient stimulation. We saw it at 4, at 5, and also at 6 atmospheres. This big surge you're seeing here is due to the fact that most of the animals are starting to seize within 4 minutes of going to the higher pressure. So now if we go on further on down, well, summary. So respiration usually decreases during normal baric hyperoxia in the majority of the animals tested. That's that inhibition of the peripheral chemoreceptors. Then there's an early ventilatory stimulation, and eventually that goes away as the animal blows off CO2. Then there's a later response, and this is the one which we think is a physio marker for the onset of seizure. So here's tidal volume, frequency, and minute ventilation. And you can see here, this is 5, 10, 15 minutes. And what we did was we lined up all, because the animals had varying latencies to seizures, we took the point where we said that they had just begun seizure, and we superimposed that here, and then started working backwards until too many animals had dropped out, and there really wasn't enough to include to average. And what we consistently found was then, regardless of the latency to seizure, was that from the beginning, about 8 minutes before, you can see this rise in minute ventilation. And you could also see that at 5 atmospheres. At 6 atmospheres, you can't really see it, because the problem you have is this arrow is telling you where on average most of the animals began seizing. Or I should say they seized within the first 5 minutes. So this is kind of a mess in here. So using our ventilation definitely works at 4 and 5 atmospheres. I know some people use 6 atmospheres in anesthetized animals because they think that's necessary. I know they think that overcomes the anesthesia. I think in the awake animals, 6 atmospheres is just too much for at least in our hands. So we do everything now at 4 and 5 atmospheres. So in addition, we said, okay, if we think that this ventilation stimulation is occurring through oxidation and acidosis, both stimulating the same population of cell, we should see some link between the hypercapnic ventilatory response and the hyperoxic ventilatory response. So if an animal has a real high CO2 response, it should have a really high oxygen response, we thought, if they're working through the same neurons. So in the same animals, we also did their CO2 responses to 5% CO2 here. And we analyzed that, and what we found, we weren't quite sure, since there was some variability, and I think it's probably due to the fact we're using poikilocapnic hyperoxia, not regulating end-tidal CO2. You can see we got everything from a very strong correlation to, well, you know, not so much. This is 4 minutes prior to seizure at 4 and 5 atmospheres, and 2 minutes prior to seizure at 4 and 5 atmospheres. So using the poikilocapnic hyperoxia, we get a relation. It's suggesting the hypothesis that we're simulating the same population of neurons with O2 and CO2. A previous study in humans that actually used isocapnic hyperoxia and kept the end-tidal CO2 constant. You can see there was a very strong correlation here between ventilatory response to CO2 and ventilatory response to oxygen. So that's the longest part of the talk. There's 2 more things I'd like to cover here in the 7 minutes I have. And that's the oxidative preconditioning using hyperbaric oxygen, a low level of hyperbaric oxygen, and hypobaric hypoxia. And then also what we call hyperbaric preconditioning using normoxic gases. And of course we hypothesized there'd be no effect here, and we hypothesized there would be an effect here. And so this is what we did. Just as an example, this is showing you one of the gas mixtures. This is the 2 atmospheres of oxygen for an hour on day 0, or on time 0, 48 hours later for another hour, 96 hours later for another hour, and then 24 hours later, we dove to 5 atmospheres to see if, and the thought here is that you've upregulated endogenous antioxidants by triggering ROS production at each of these earlier time points. And we use some other gases, heliox or hypobaric hypoxia here for an hour. So it was the same time exposures, and here's what we got. A lot of data here. Let's look at the faces. Here's the control data, and down here I'm showing you what the inspired PO2 was during the preconditioning phase and what the barometric pressure was at the preconditioning phase. And so in response to 5 atmospheres, we find that the animals, when preconditioned with just air, they seize in just under 30 minutes here. And what we found with HBO was essentially the same results, 2 atmospheres oxygen. There's no difference. We tried also 1 atmosphere oxygen, reason being we wanted to try something without hyperbaric pressure present. You'll see why that is in a second. And these were not statistically different. We then said, well, let's do tests for the convection pressure, and we predicted there'd be no response, but as you can see, there was a very strong response. So what we saw with a normoxic mixture of helium and oxygen, that the animal now, after 3 of these treatments, was very sensitive to 5 atmospheres and seized almost immediately with 2.2 atmospheres of oxygen and nitrogen balance. You can see that also he seized very quickly. We did 2 atmospheres of just air, and you can see he seized quickly also. But what's interesting is as we're kind of raising the oxygen from here to here, I'm wondering if there's maybe not some sort of an oxidative preconditioning effect that's being overridden by the pressure effect we're seeing. We then said, let's try hypobaric hypoxia, and you can see here it went in the other direction. And so it had delayed the onset of seizures. So then we said, well, is it the lower pressure opposite to this, or is it the hypoxia that's doing it? Well, when we did the hypoxia at 1 atmosphere, same level of hypoxia, there was no difference. So it's definitely a pressure effect. That's what we've got over here. So what we're seeing is high pressure preconditioning is actually increasing the risk for seizure, and flying before you dive is actually giving you some protection. So everyone knows you don't fly after you dive, but maybe flying before you dive is useful. And so we were quite excited by that. And so then if we took the gases where we used all balance of nitrogen, you can see here at a half an atmosphere, 1 atmosphere, and 2 atmospheres, the preconditioning effect on the animal's response to 5 atmospheres was dropping off dramatically as we increased the preconditioning pressure. So question is what is causing this? I don't know yet. It's taken us quite a lot of work just to get to this point, and obviously what we would like to do is precondition animals, start taking slices from them and looking at the cellular level what's going on, and then of course at the signaling level too. But what's clear is that the oxygen sensitivity, how the membranes responding to ROS and to RNS and making the animal have seizures, is being modulated by this preconditioning pressure. Hyperbaric pressure is causing it to become more sensitive to oxygen, and preconditioning at altitude is causing it to be less sensitive and actually giving you some neuroprotection. You know, what's going on here at the membrane, what's going on at the mitochondrion, what's going on, I don't show it on here, but I should, the synapse. We saw Ben's talk this morning of the effect of pressures, the same levels of pressure on calcium release. And so we don't know the mechanism, but this is, we think, a very exciting area to look at. And what supports that, I believe, these data is that we'd already found that neurons in this area were sensitive to pressure, small pressures. In fact, this was something that I remember one of the first times Rami and I ever talked. He was surprised by these data, that just a few atmospheres of pressure could stimulate neurons, and we do find that. We find that it's an intrinsic property to the cell. Here, if we block synaptic input, they continue to be stimulated by helium at constant oxygen, constant CO2. Yet, not all cells respond to pressure. So, in fact, most cells don't. Almost 70% of them in the solitary complex were pressure insensitive. You can see this was a long exposure here. So it's a unique property of a specific population of neurons. Which cells exactly they are, well, that's part of the search we're on. Okay, and then just briefly, as a way of introducing the next talk, ingesting ketone esters to see if you could delay seizures. I'm in my last minute, right? Yep. Yeah. And ketogenic diet and starving, as Dom will tell you, has been used to treat drug-resistant epilepsy. Well, starving hasn't been used, but the production of ketones has. And he'll be going through all this, and I'll let him suffer that. And but the point, what I wanted to point out is that the ketone bodies are an alternative energy source, and a consequence is it begins to quench ROS, reduce reactive oxygen species, increases metabolism, increases oxygen consumption, and that seems to be part of the neuroprotective component. But the main thing here is that if you orally gavage water versus ketone ester 30 minutes before you dive them, you can see that the time to seizure is increased, actually on average, by over 500%. Oh. So that's, we're very excited about this. So that's where we are. In summary, physio marker we think is hyperoxic hyperventilation, and we want to be looking next at isocapnic hyperoxia, because we think a little bit of CO2 retention would be good since that happens in diving, and we think that that might even give us a bigger ventilatory response preceding seizure. Oxidative preconditioning in our hands, it does not provide neuroprotection, but hypobaric preconditioning does, delays it by 38 to 56%, ketone esters by over 500%, but actually we have to worry about pulmonary oxygen toxicity now. The oxygen exposures are so long, we start to see evidence of breathing problems. So, on the other end of the continuum here, hyperbaric preconditioning is definitely going to accelerate the risk for oxygen toxicity. So, thank you for your time, your attention, and these are the people back home who you've seen today, but I wanted to acknowledge them again, especially this good-looking guy. Thank you.
Thank you very much. We are open to one question. Yes, Danny.
Since oxygen toxicity is very rare in hyperbaric treatment, and the main interest may be in diving. How do you think all this would be modulated by exercise? Would you see this hyperoxic hyperventilation?
Well, yeah. So that's in the manuscript we've written, we've said that the hyperoxic hyperventilation is, in our model, is useful for predicting seizure in an animal at rest. And because that's the conditions we had. The rat was just sitting there free and untethered and not doing anything. And that's the question we've had in the lab, is what happens in the animal or the diver who is exercising and swimming hard and doing something. We don't know what's going to happen. But the step I want to do here is to repeat these studies with a little bit of CO2 retention, because I think that's probably even a better model. I think normal divers are going to have a little bit of CO2 retention just from the dead space and the mechanics of the breathing and the gas density. So I think, well, we already know that the ventilatory response is much bigger under those conditions where CO2 is prevented from dropping due to the hyperventilation. So I think we'll see an even bigger response occurring even sooner. That's what I'm hypothesizing. I think after that, then, what you would want to do is introduce it into an animal that you've got running on a treadmill or something and see what happens. But yeah, how good this would work, it may fall all apart when the exercise is going on. But certainly for a patient, it would be useful.
Thank you very much.